Go to mesh. For primitive, there is a mesh plane, and we can specify the boundary of the mesh and how are going to divide horizontally and vertically. Let me draw this mesh upright. So I switch to the front view. So now it is on the front view. And here I want to define the boundary of the mesh. So say set one rectangle, click one corner, and then the next corner. So now we have this mesh, and the default value for width is W and H. Oh, maybe I should do it the other way. Okay. Sorry. Let me change another way to do it. Go to curve. First, we draw a rectangle. Draw a rectangle, primitive rectangle. Okay, we need to have a base plane because I want to make it upright. So I go to vector and then find the XZ plane and use XZ plane to draw the rectangle. Okay, I think the default X and Y are like this, but I want to specify different lengths and width. So I use a slider. Maybe I say 5 and 2. Oh, let me make it 10. Okay. So now I have this rectangle, and then I'm going to use this rectangle to be the boundary of the mesh. Okay. And then I use the X size and Y size to dissect the entire rectangle into faces for the mesh. So that in this case, I will be always sure that the size of each cell is 1 to 1. So for example, if I increase the Y size, okay, so it simply draws like a chessboard pattern, or I can change it, right? Okay, so I'm going to define this mesh as a kind of membrane structure, okay, with the kind of with a similar behavior, just like the string that we define. Okay. So now we have this mesh. Okay, what we can do first, of course, we want to maintain the length of all the edges. So we go to Kangaroo 2, and there is a group of components deal with the behavior of the mesh. There is edge length. So we maintain all the edge lengths to it. So it creates a set of, okay, so let's start to do the simulation right away. And I think we always need this set of component, right? So we simply copy and paste and then use it here. Okay, we don't need that many end slots, so we remove it and then use this to replace it. Now it shows, right? And we start the simulation. Oh, sorry. I need to grab it, right? So I need to add one more force object, which is to grab it here. So after I add it, now I can grab it. Okay, but it has no control on the angle between these edges. The only constraint is that the length of the edge will be maintained, okay, when it is possible. Okay, so this is not so funny. Okay, what we can do? What do you think? Any suggestion? angles. Okay, so the angles between these edges, right? So what we can do regarding mesh, we go to analyze, we can retrieve the edges. Here, mesh edges. Okay, first I do the easiest way, okay? What is E1? We take a look at this yellow window. It's a naked edge. So it is the boundary. They are the boundary of this mesh. Okay. So if we set the angle constraint on this boundary edge, okay, let's see what kind of behavior it will get. So the same, we need to have a shift, right? Shift this. And because it is closed, right, so we don't need to reset the rep. And then we use this angle constraint of Kangaroo 2. Angle constraint Kangaroo 2. But then what angle? What is the rest angle? In some cases, that's 0 degree, right? Because one segment is parallel to the next segment. But in some cases, it's 90 degree. So we need to analyze the initial angle between consecutive edges. Okay, what can we do? Before we are able to decide the rest angle, we need to calculate the angle between every pair of these edges. Okay. So what we can do? We have to find out the vector, right? Because in the vector here, there's a component that we can calculate the angle between two vectors here. But we need to find out the vector. And you see the line is not the vector. The line has a starting point, but the vector has no starting position. It has only direction. So what we need to do is to use the starting point and the end point of this line segment to calculate the direction of this line, which is the vector. So we go to curve, we get, sorry, not this one. We get the starting point and the end point. And also we do the same thing for the shifted list. And then we need to use vector, create vector. Oh no, sorry, not this one. Here, this one. Start point, end points. Okay. Start point and end points. Now we calculate the angle between these two vectors and then use this for the rest angle. Okay, there are two outputs. Because to calculate, to analyze the angle between two vectors, we can go from either clockwise direction or counterclockwise. Okay, so here one output shows you the angle calculated in one direction, and the R calculate the angle for the other direction. Okay, so like here, the first two, you have 0.5 pi, and for the rest, as far as we can see, they are all 0, right? So if you go down, you see the first one is 1.5 pi. So if you add up 1.5 with 0.5, you get 2 pi, which is the full circle. And the rest, they have 2 pi. Okay, so now we take the first one. line A, line B. Line A is this one, line B is the shifted. Okay, now we are ready. Okay, now we need more spaces here. We need to add one more slot. Okay. Okay, see, now the boundary is kind of forced. Try to keep the boundary segments maintain its original the angle between all consecutive. But still we have no control, absolutely no control for the internal edges, right? So how about if we take all the faces, and for each face we have 4 edges, right? And then we do the same thing, calculate the initial angle between these edges and then set a constraint to maintain all of them. Okay, so maybe now we can try to do another thing. Here is the mesh. Okay, I would like to do one thing which is not necessary, but I think it will make your program clearer. So this is the mesh I am going to work on. So I simply use this mesh component and then move it somewhere, okay, some clean area. And if you like, you can set the wire display to be hidden so that it disappears when it is not selected. Okay, but here you have this sign showing that it's remotely connected to other component. And when you select it, it shows the link. Okay, otherwise it is hidden. So to make the whole working area clearer. So we start from here, and we want to find out all the faces, the boundary of all faces. We go to Mesh, Analyze, Mesh Boundaries. And let's check what do we get. So they are all polyline curves. Okay, and we need to find out every individual line segment in this boundary. So we explode it, go to curve, explode, and let's see what happened. So every cell we find the 4 line segment, and we want to do the same thing, right? First a shift. Actually we can copy this part. We can copy this part and then reuse it. All these line segments, we find the starting position and the end position, and yeah. The situation is more complicated because now we have list of lines in different branches. Okay, maybe let me try to simplify it. I want to make sure if this is going to get into trouble. Yeah, I think it is fine. And you see everyone is 90 degrees because the entire grid structure consists of squares. Okay, so I think it is ready. So now we can add this set of force object to the simulation. Okay, it's a mess because we need to reset it. Go to perspective view, and now we can drag. Sorry, something is wrong. I have to check it. Something is wrong. What is wrong? Okay, let me pause here. I copied this from this part, and I forget to replace this connection. So this line B is from the shifted list, right? And this should be the original here. Okay, so I have to reconnect this part. Now let's see. Yeah. Now it's act more like a membrane, right? Okay. And one more thing I want to add. How can I do if I want to show the mesh? Okay. So here we have our original mesh object. Okay. And I want to show it, so I go to Kangaroo 2, and here this light bulb is to show it. Okay. If you want to show something, usually it means that you want to have further process on it after the simulation. So I would suggest that you always have the show object on the top of everything. So if you do this, then we can see what you get from this output of this simulation. You see, the one that you put on top will be always also on top. Okay, and the entire tree structure will be the same as the tree structure created by this ny. So that's the reason why we use ny. And because we might want to work on this mesh, so I also always put this show on top, so that you are sure that you always get it as the first one, the first branch. So now we can explore the output of the output tree, explode tree, and then click the right mouse button to make sure that it matches output. And we know that the mesh, we can always get it from the first branch. So this is the thing that we actually want to show for the simulation. We don't want to see all the rest, these points and lines, or we only want to see the mesh. Okay, it's no problem. So now we can do it like this. Okay, now you have this planar sheet, and also you can, in Kangaroo, you can blow wind onto it, so it will be flipping like a flag. Okay, or you can hang it on the wall and then apply gravity onto it, so it will fall down. Okay, and then you blow winds onto it, so you can see how it reacts. Okay, let's take a break for 5 minutes, and I will terminate this recording here.